Hello all, I'm Ann Buckhouse. I'm Education and Training Manager at Pawsey. You would have received a few emails and invites from me. Prior to kicking off and getting started for the day, I would like to acknowledge the traditional custodians of the land on which Pawsey is located, and that is the Whadjuk people of the Noongar Nation. And I would like to pay respects to elders past and present, and I'd like to extend that acknowledgement and respect to Torres Strait Islanders and Aboriginal individuals joining the call and from all the lands from which we're dialing in from here in Australia. Other than that, I hope you enjoy the day.
All right, why don't we get started, Norbert?
Right, so who is ready for Python? Yeah, so
Well,
the work plan is that yesterday we had the code producing an ADIOS output, right? And I trust everyone did their homework and added the second variable into that output. If not, that's okay, we are not using it, but tell us if you have any comments on that, on the homework.
Well, I think,
or if, yeah, so just on the right side, and then we move on to the read side.
I think the real question is, A, did anyone have any problems trying to figure out how to add another variable? And B, from the functions that we provide, the API, you know, does anyone have any feedback, positive or negative, that we could use? Like if you're familiar with HDF5, how is it going over to ADIOS or, you know, MPIO or whatever? It's just basically trying to get some feedback to us.
I at least I can comment on from someone who's done a bunch of HDF5. I mean, they're similar with some small dissimilarities, but like the overall way I would tackle a problem seems very similar. The main thing is I haven't tried really mucking about with steps and the streaming yet, which is obviously not something you do in HDF5. But overall, I mean, it seems pretty good. That would be the main thing, is trying to muck around with steps and flushing, that I'll try.
Okay, well, we will get into that today.
Cool.
That's exactly one of the concepts after we get reading. Because once we have reading, then we can get into steps. So
Right, so I guess instead of talking, then let's start working on the Python part. It basically, I'm going to show, or we are going to use the low-level Python API in ADIOS, which is generated with PyBind from the C++ API. So it's basically you are learning the C++ read API as well, because it looks the same. So it's not really following the Python philosophy. It's a C++ API for C++ codes, but it gives you the full arsenal of the operations that you can do in Python. So that's what we are going to do. So let's go set up our environment again. So
share the screen first. Or you are.
I'm sharing the screen.
Okay, great.
And okay, so let's set up our environment. Don't forget to source the environment script, right? In the first page of.
Are you going to sit?
No, I'm just trying to look for it. So, you know, you have this PDF, the first page, to set up your environment. That's you have to source in every single terminal you have. And then I at least lost my connection. Okay.
That's what I was trying to do.
So I can just start. Let's source our environment. Anyone knows why spec is so slow? It's just loading the spec modules, and that's why it's so slow and so slow. Okay, so we created our code yesterday. I ran it last with ADIOS I, so I need a allocation to run it again and get an ADIOS file. So, right, my output will be, my choice of name is grayscale.bp. Oh, that's not. Okay, so yeah, my engine was before, it's the default engine anyway right now. And now I can use BPLS on gs.bp is here in the file. Right? As you see, it's a directory. It's the same size as the ADIOS I file. And so if we run BPLS, then we have, I have one variable u, you added the other variable v, right? So we have 100 steps of a 64 cube array, and we have the step over, which runs from 10 to 1000. So those were the iterations of the simulation. If you haven't tried it, BPLS, Pascal should be interested in this. The capital D prints the decomposition of each variable and for every step. So what we can see is every process in every block that was written. So every process did one put. So every process produced one block here. And we can look at its offsets and sizes information here to check if the decomposition looks all right. So in the beginning of developing the code, this is the way to basically check that, yeah, you did the decomposition the way you expected to do it, and you did it right. And then there is a min max for every single block separately. So if you have problem in a computation, you see somewhere not a number, you can hunt down which process had that in the data before starting reading a giant data set. So it just could be useful or not. Otherwise, BPLS is just a tool to read any pieces of the data. So it has a few options. You can always look at that. The trick is that we want to dump with a small d variable like the u. And then since it's a 64 cube, that's just too big. So for the sake of tutorial, we could just say the way of reading these as like a 4D array, setting up first offset in the steps. So we have 100 steps, so we can like print out the first step from the first step, and somewhere in the middle, so from the 31 offset, we can just dump a single step and the 2 by 2 by 2 cube, and just printing 2 numbers on the screen. Then we can get that 8 numbers from the center of the 3D cube, which was produced by 8 process. So each value is coming from a different block, from a different process. So you can read arbitrary slices of your data and then print either this way or without the indexes, this format. So whichever better for your post processing. If you still do something with text-based processing, then it's available here. Basically, that's all I wanted to show about BPLS. So now we have a data set, right? And we want to do the same thing as the gsplot Python script. I don't know if any one of you looked at it already, the MPIIO based plotter. So it's just a serial Python script. It will read the midsection of 2D slice from this variable. So in the center of the first dimension, so it's 32, and it reads the 64 square slice, and then just plot it in a pseudo color map. So that's what we are going to do to work on that script. So have a terminal where you can work on this, and we just go through the source, my source, no, my software, and my code. The ADIOS VM, tutorial, my code. So wherever you copy the tutorial code, we go into our code, and the plot directory has this gsplot.py that is still doing the MPIIO stuff. This is what we need to work on. And as usual, so if you don't have a good environment to edit code, like I use Visual Studio Code, which has C++ and Python extensions. I actually didn't set up the Python extension, but then it gives, it's easier to see the function parameters. It helps you with stuff. In this VI, I don't know how to set that up. So if you know, you are lucky. So I usually, what I do is that in a different terminal, I just run Python. I will just run Python as a interpreter, import ADIOS, and then I can at least check the function names. The other place to look for API is you have this link. You have this link in the presentation. Is in our documentation is on read the docs. Right, so this is ADIOS to read the docs IO. And we have the full APIs documented here. And the C++ and Python's is auto-generated, so it's hopefully correct. But you might find problems there. And so you can start looking at this. Basically, what we have is a few classes. And it's the same thing as the C++. So we have an ADIOS class, an IO class, an engine class, variables, attributes. And each has a few functions to use. So you can look for guidance here. And for just preparing for this tutorial, we found that the MPI argument versions of the functions are missing. So actually read the docs doesn't parse the MPI flags, and it just parses the serial version of the API. So so that's the only thing you don't find in the APIs right now. We need to fix that, but otherwise we have the full set here. So that's one way to look at it. And okay, so if I go to my Scratch, where we have the installed, where we have the data, we can play around with this. Right? So we have gs.bp. If you run Python, then basically you need NumPy. So you import NumPy, and you import ADIOS 2. And if you are doing parallel Python, then you need MPI for Pi. We are not going to use that, but so the standard setup. So now we have ADIOS functions, and then we could say the same thing as we did in the C++ code. We could say, like, let's create an ADIOS object. And well, we either pass something or not. We have an ADIOS object, then we can create an IO object. A dot. And so now I could actually use the tab to find the function, declare IO. And well, that's what we see in the Python editor is to see the arguments, I think.
Can you use a Python notebook?
Hmm?
Do they have a notebook?
Exam question, answer was no.
Oh,
Really, right? Or you can, but you could.
Oscar?
So yeah, I mean that's another way if you can run a Python notebook and Tinker in that one. But
they wrote something, connect the Pawsey remote file system.
Fish protocol. Okay. Okay. Thank you for that information. I never even heard about fish protocol. So that's good. So you can actually use VS Code editing code on Setonix. That's great.
Yeah,
I like
I've got-
VS Code.
I've got
I didn't know you,
direct
but you are
access.
doing it. Okay.
But I'm connected directly to Setonix through, not through Magnus. So that might.
Joy, probably that's good. And so your VS Code, yeah, okay, so okay, Susan,
SSH.
I tried SSH, but then VS Code doesn't support the architecture, so it couldn't.
It's weird.
Wait, does the Setonix works?
Yeah.
Okay.
For my normal username and all, it all works. It's just that this one has got slightly different, and I just go via Magnus for now.
Oh, okay.
But usually, yeah, everything works.
Oh, okay. So if you are editing, then you should have a good time, right?
Yeah.
Okay. Okay. Good. Then you don't even need to struggle here that much. So let's follow yes, you can follow the slides on your own. From slide 29, I think. Right, and just go change the gsplot code. I'm going to do the same and talk, but you don't need to listen to me. You can just look at the slides and follow this whole thing. So in the script, you need matplotlib as well because we want to plot something. And so you see the first thing is to import ADIOS in the script and do these lines of creating the ADIOS object, the IO object, and then opening the file. All this code in the existing code is the Python for processing a binary file, where we know that the header, which is 3 8-byte integers, describe the size. So this part of the code opens up a This part opens up a binary file, reads the first 3 numbers, and then gets the size with the shape as a 3-element list. And then it also checks the file size, the file size with the fstat, and then calculates, okay, how many of the 64-cube U variable is contained here, and that's the number of steps. So that was not stored as a number, it is calculated from the file size. So we don't need any of those, right? We just want to open the ADIOS file. So that's the first thing we need to do in our code.
Quick question, Norbert, just to remind myself, in the ADIOS XML file, the only thing that would relate to reading would have been the timeout. Is that correct? Because I remember in the XML you had little stuff listed so that it would time out if it didn't connect to the appropriate ADIOS stream. Otherwise, is it necessary to have the ADIOS XML? You could just specify, you could just generate an ADIOS object, right? And then declare.
So in the terminal, I just created an ADIOS object without config file, right?
Yeah.
So there is no settings for my IO object at all, and just created a random name for it. There is no settings for it. But the purpose of the tutorial is that this Python code should be related to the simulation code. And if the config file is where you set the production engine. So like I could have HDF5 file, I could use SST staging. And if the Python code can also pick that up, that engine, and be able to open an HDF5 version of the file, or connect with SST and run in situ without producing file. So it's not just the timeout, it's really since we use the same IO name, simulation output, and use the same config file, both sides, the writer and the reader, is using the same engine and the same settings. So if you don't use the XML, right, you just created an ADIOS object without config file, the default will be using BP4. And if you start running the simulation with SST, it will wait for someone to connect and read, but no one, even if you run your Python script, it's expecting a BP file because no one told it to use SST. With HDF5 is different. If you give it a HDF5 ADIOS and HDF5 file, then it will figure that that's not good for a BP engine and it will open the HDF5 engine by default. So that works, but otherwise you really need these XML, the same configuration, both on the write and the read side. So for, yeah, and so for basically for in-situ pipelines, this is basically the only way to do it. Okay, Pascal, did I answer your question?
Yes, that was perfect. Thanks.
Okay. Okay, so go ahead, edit your code. So we needed importing ADIOS, and then in the main function here, the sections that is doing the MPIO business. You don't need any of those. Right? See if I can just copy paste. Can I copy paste? No, I can't. So I have to type everything. Okay, so this line is tricky. There is 4 ADIOS in the same line. So you get it right. So ADIOS 2 is the module we have. Capital ADIOS is the main object. And I just happen to name my Python variable as small ADIOS, just to confuse everyone. Okay, and then create an IO function object. You have very quiet keyboard. I don't hear anyone typing, so that you guys are progressing.
Out of curiosity, Norbert, is there a way to get the keys that have been set for the IO from the ADIOS object quickly? If there's any, if you were, doing interactive session and you couldn't remember the name of the set of outputs sort of keys, does the ADIOS object allow you to get those defined outputs, the names of those? Like simulation output. I think there's a couple more in the XML file.
Oh, the names of what the names are? No.
Yeah. Okay.
I don't know that. Are you talking about the options that can be used for an engine, or are you talking about the list of
the list that have been in? I mean, you can always look at the XML file, but I'm just wondering if there's a way to in Python just quickly get all the.
Well, I don't know.
Okay.
Might be. I don't know. Maybe the ADIOS object has a function for that, but I actually don't know. Never occurred to me. I want to use that. Okay, so in this Python script, this args.instream is the name of the file. I mean the incoming stream, and then we need to use read mode. So this will open up our file. But we have no information. So what we are going to do here is to write a proper in situ Python script to go through the incoming stream step by step. So there are 2 ways to approach this problem. There is a file reading mode in ADIOS called read random access, which basically what BPLS does as a tool. It opens up a file, it sees all the steps at once. So it goes through, processes all the metadata in the entire data set, and then it presents you, okay, you have 100 steps of variable u, you have 100 steps of step variable. Once you start putting different variables in different steps, you will get weird numbers. You have 34 of U and you have 37 of steps, and good luck finding the match. But it's an easy way to process the file completely. So you just open it up. So we are using the read mode in this script, which is the going step by step. It only opens the file and gives you the very first step. And then, I mean, actually it doesn't give you this. You have to start begin step, end step to get to the first step, and then the second step and the third step. And then you can process it, the whole thing step by step. If that fits your analysis, that's good. If it's not like that, you want to think just all of it and be able to read any step, jump around and read the 50th step and then go back, read the 20th step. You can do that in the read random access mode. And so then you would have a for loop, you could use how many steps do I have for that variable, and then you just go and do a for loop on that. That's the way to do it. But for any in situ where the stream is being generated, you actually don't know how many steps you will have. You can write the code, be able to connect to this producer, and as the steps are coming in, you can process them one by one and wait, have a timeout waiting for a half an hour, or 5 days for the next step coming in. And you can decide what happens if you don't get a response. And when the stream ends, when the producer closes the stream, then there is no more steps. So your loop will just figure that out. So what's on the presentation is the while loop, and we will exit the while loop when the stream is terminated. So there are begin step will give us a status. A file-based reading, it will give us OK for 100 steps, and then at the end it will say terminated. In a stream, you could get saying not ready. Maybe there's a next slide. Okay, so we just use the let's exit when it's not OK. I thought I put the other one in the slide, but apparently I didn't do it. Just for the simplicity, processing. Okay, so since our Python script is much slower than the Grayscale example, we will never experience that status that it's not ready. By the time the Python script ready, the simulation would produce 10 steps. So the simple just for the tutorial, it's just fine to check the status not OK, and then break the loop.
What happens if you reach the wall time first?
A wall time of
Of the processing. So if, for example,
your job, you mean?
of the job, yeah, or say in the allocated environment, interactive environment, you're doing all this and then you're just running to see, and in the middle of it, the cluster decides, right, you've reached the end and cuts you off. What would happen then?
Well, you got cut off.
Yes.
Your application will basically abort, right?
Yes. So what would happen with this? Would it, when we rerun it, would it continue where it left off, or does it start from the beginning?
Well, yes, none of them. I mean, it totally depends on. So if you rerun it on an existing file, it starts from the beginning. If you use staging where there is no data, then whatever the simulation restarts from and starts producing data, that's what you are going to get.
Right.
But so it's not, in none of the cases will start off where it left. It depends on the producer. But so if you open up a file, you always start from the beginning. It doesn't remember in a file that someone was reading halfway. Unless you do checkpointing of your Python script and saying, I'm done 50, next time if I have to restart, I will start from 51. Right. Okay. That would be up to you. So there is no information to where to restart from. Okay. Okay. So what should we look at? So okay. So in the loop, right. So your loop is we just stop counting the steps we have and call begin step. And then we get a status. And if the status is not okay, we can break this loop. You can always go to the GS ADIOS II version of the tutorial in the source code and then look at the full loop and just copy paste, or the other slides. Other slides have, I have this example here, right? So this would be a proper loop. There could be end of stream, so it's not terminated, end of stream. Then you know that there is no more data coming in. You can safely wrap up. Not ready means is that the producer is behind of your request. You process too fast and then you need to wait. This is really how much you sleep here or what you set your timeout. So begin step has a timeout. So it's not immediately returning. But in this case, since you don't set a timeout, it immediately returns if there is no steps available and gives you not ready. So you decide what to do at that time. And you could get other error when there is really something wrong. So that's where things went wrong on the stream.
Okay.
So then that you will not recover from that. So it's just really, okay, what do I do here? Do I do my checkpoint and hope you can restart from here or manage your error or whatever reason? But it's end of story if you have other errors in the stream. And then, so once you are in a step, you will finish with end step, right? In the between begin step and step, you can use end step to get the stepping of the stream. And so now we need to talk about how many steps we have. We have a while loop here. So we have a steps for that, right? These steps looks, if you have not ready, you may have longer money, more. So you have that number inside the Python script. Then we have the incoming stream, and that starts from the step 0. So you got the step 0, then step 1, then step 2, then step 77. What can happen is that if the consumer is late, too slow, and the streaming is set up in a way that the producer is not going to wait, instead it will throw away data, then you don't get consecutive steps, you get some steps later. So that's a potentially different value. In our run, of course, when we process from a file, it goes through each step, so you don't get a skip in the steps. So these two steps will be the same. And then the third step is reading the value of the step variable in the input stream, which is basically the user specified value of the iteration. So that's the third value. In the binary gsplot version, there is only one single step saying, right? Because it's just processing that file and that value is always the same. And we didn't save the step as a variable there, so there is nothing to print there. But in this Python script that you edit, you have 3 steps. You have your own counter in this loop, then you use the current step to get the stepping number in the incoming stream. And then in next slide is you read in the variable step and get the value of that, what the iteration was in the simulation. Okay. So yeah, actually, I forgot what do we do with the example. Right. Okay. So the next very useful function is to get the list of variables. If you want a tool that you don't know your variables, you want to discover them, then you can get a dictionary. The key is the name of the variable, and then it has a few entries to it. So let's quickly do this. Show you interactively what it means. So if I open es.bp, so now we have a file open. First, I need a begin step. Okay, we got an okay, and then current step 0 and dictionary, the IO available variables. So now, as you see, this dictionary has two elements, the U and the step. And you have a few attributes. The available steps count tell you how many steps you have. The min max is stored there, and the shape. And then there is a boolean for, is it a single value, like the step is a single value, or false when you have an array. Just a different way of, so for the single value, the shape is empty. So both it's in, and then you get the type. So basically from this you can do whatever. In general, you get what you want. And so one easy way to get the value of the step in this example is that I get the list of variables and then use the step, look for the steps, min, and then oh, sorry, that's the, yeah. So in this, since the scalar, this is a single value, and I'm looking at a single step, but I don't have access all the 100 step values across the entire data set. I'm just seeing a single value. So I know that the min max is the same as the value itself. I'm just getting the min value. So I didn't touch the file. After opening the file, processing the metadata, having the min max values of each variables and array, without touching the file, I'm just getting the value of the step. So this is just, just as curiosity here, or it could be useful when you process a lot of scalars. You don't need to actually go to the file and read in anything. So that's one thing, but for an array, of course, so now we have a loop and we haven't read the shape of the variable yet, so we need to discover that, right? So from the information, we have to use the inquiry. Okay, so forget about the dictionary. That's one way to get the shape. The other one is, if we want to read it, we have to get the variable object. So we do inquire variable. I don't really have a pointer to show, right? This, right? This. So inquire variable, we will get the variable object, and now we have all the functions of the variable to discover. And there is one as a shape. This will return a Python list for us. The other way is to what was it? Use like the dictionary. Then you have, this is a string, right? So you would have string processing to process it. So it's not that comfortable, not that convenient. So it's easier to just get inquiry, and then for the reading you will need it, get the shape, then do a decomposition. So this whole example inside the loop is about doing a XY or ZY or XZ slice of the array, not a 64 square 2D slice. And so you have these ifs for the 3 different dimensions where we cut, and we have to define how to read the data. The MPI IO version reads in the entire 64 cube data. It doesn't figure out how to read, because well, I don't have slides for it, but I hope you appreciate or you can imagine it, right? You have a 64 cube contiguously stored dump of data in the file. If you want to read a 64 square slice in the YZ direction, then it's easy. You can calculate where to seek and read the 64 times 64 number of doubles, and you are good to go. If you read a slice across the cube, Now you have a hard time because you would have to do a double loop of seeking and reading pieces and then assembling your data in memory, right? So who would do that? So instead you just read entire 64 cube and then in NumPy you slice it. That's very simple. As long as your data is smallish, that is, who cares? But in ADIOS, we will do it properly. We simply calculate which 2D slice we want, and then we'll tell ADIOS to deliver it us. And then, of course, ADIOS implementation does this seeking and getting in the pieces for you and assembling the array for you. So the code is simply saying, well, the np empty is this NumPy empty is the malloc equivalent in NumPy. So we allocate a 64 by 64 array and don't initialize. It's a double array, right? So data is a pointer that we can give it to ADIOS, and then we set for the variable, the ADIOS variable object, we specify the set selection. So we have a 3D array, and so we need to seek into the middle in 1 dimension and then 0, 0 beginning offset. And then the size is 1 by 64 by 64, right? So that's the set selection function doing it. So here in the room, raise your hand if you understand what I was saying. So if you don't have questions. Yep. Just want to make sure so that you parse it in your mind. Since I'm not editing the code, I'm a little bit faster, but that means you may forget. So this is a tuple of 2 3-dimensional, 3-element arrays saying where to start and how much to read. So we read a 1 by 64 by 64. And then we tell ADIOS to get this variable into this data pointer. And we use the sync mode to say, I want it now. So this function, after returns, we will have the data in the variable type, NumPy variable data. So after the get function with sync mode basically gets you the data immediately. Don't forget it. If you don't have this option, the default one is deferred mode, which means you are just declaring to ADIOS to get the data from the file for this variable, which is related to the variable u, with this selection into this data pointer at some point in end step, basically. And then so you can schedule a lot of gets for many variables, and then in end step you say, okay, get me now all of it. But we have this if then else, and we do the plotting, so we just get it immediately here. And then we just call the plot function to do that 2D plotting. Right, so your homework, well, besides editing the whole thing, and then the homework is to get the X, Y, and XZ planes. That's basically playing with which shape you use, although you can't go wrong with the 64 cube array. And then changing the set selection, which 2D slice you want. And the reward is funny. This is a very symmetric setup. So in every dimension, you should get the same image. So you won't, if you mess up, you won't know. Yeah, that's what it is.
Norbert, I have a question about the set selection. So right now you just have the list that's a 3-dimensional list of the start and endpoints, but could you provide a subsampling of indices that you want to select? So like, let's say you want to, for some reason, your selection is every odd cell. It's probably in the documentation how to do that, but could you provide an array that just says all these indices?
Let's Scott answer this favorite question from HDF5 users. Yeah, please.
I'm not answering it.
Oh, you're not answering it. Okay. I wanted him to answer it. Yeah, so basically you are asking if we have hyperslabs. And no, we don't.
Okay.
And we don't have it on purpose. Using hyperslabs ruins the performance.
Yes.
And of course, so why would we give you that functionality? So it's a convenient way of ruining your performance.
I'm sorry, I missed the question. So what is a
right?
hyperslab?
So Well, so we are on, as you, we have this 3D cube, and what we read is basically logically, virtually a fully contiguous slice of the data. But there are patterns like you have a matrix and you only want to get every other column and every other row. So you reduce your read by 1/4. You only want to get every 4th point in the 2D space, or in 3D, every 8th point, right? So you want to read much less because the array is too big. But the thing is, that would be if the implementation doesn't read the entire array and pick out the values one by one, then seeking on the target and reading the values point by point or row by row totally destroys your performance.
Yeah.
So it's a convenience function that lures you into using it because it promises you a very convenient way of access. But then everything goes wrong, and then you start complaining that how bad that library is.
So,
Yes.
yeah, I mean, all I'm saying is like, this is something we have struggled on. It's easy to implement. But as Norbert said, there's really 2 ways you can implement it. You could read seek. But, you know, if you do that, especially on these parallel file systems, I mean, you would be hundreds of times slower than just reading everything. So you're going to just say, you know, ADIOS is horrible because look, I'm reading less and it's taking all this extra time. So, you know, it's been a struggle because there's only been a handful of users who really said, we really want this. And once you talk to them and tell them that, try it out with HDF5, for example, see what happens. And then, of course, they want to cry for how bad it is once they have real data, not a test. So it's, I mean, it's one that, I don't know. I mean, do you guys really need it? If we put a warning, something like, this is stupid, but here it is.
Well, so I'm gonna say the reason I ask is I know it's there in ADIOS and I don't try to use it, principally because I just try to take out let's say in that example, or I was taking every odd block, I just take out what I think is a more easable slice into memory and then do my subselection on that bit of memory. I don't try to do it through the
Right.
file interface.
But that's exactly right.
Yeah.
But I'm saying that this has been a very contentious argument because like you can actually go through the vol layer of HDF5 and use ADIOS. You're limited with a lot of things we would tell you about with staging, but you can do that. But they say they will not officially support this if we don't give them the ability to say stride. And then what we don't want to do is give them the ability to stride, because then you're going to see bad performance, and HDF5 is not going to report that users are being stupid. So it's like, we don't know what to do. If you guys have input, advice, that would be great, but I don't like to do things which are really going to screw up performance and in a major way.
So the hard bit, right? So I have used stride before, but it's usually a very specific thing. And it's usually a stride in normally a 1D array that I'm just skipping every 3rd one. But for any sort of more complex pattern, I just read the block I want and then do actual selection on that block in memory, right?
ADIOS will, well, but that's what HDF5 actually does. But now again, when you do that, it takes longer.
Yeah.
So no matter what you do, it will take longer perceived to the user.
Yes. I guess my main thing is, well, so it's probably a biased perspective because I've always, since I know that it can be poor, I've just made sure that the interaction with, let's say, the file is simple. And if there's any subselection sampling, it's in code and I can check to see that, yeah, it's just a complex subsampling and I know it's going poorly. What can I do?
You're doing what we do.
Yeah.
You're doing everything that we say, that don't give users something that could really be horrible. But
I don't know
the
if someone
question
else
is-
has a different perspective, though.
I'm just
That's-
right. I'm trying to figure out, you're doing what we do, so that's cool. That's great. Does anyone have any other perspective? Like, are we missing something? Should we offer the functionality, which we can do? Should we do it? This is feedback to us. Right, and the reason why I think the group here is you guys actually work with like things like SK or real things. And this is the challenge you have when you work with a bunch of people who don't work with real things. They work with like simple benchmark codes. And it really annoys me because they keep trying to make us look bad, and I'm saying, you know, this is not the way. If someone's knowledgeable, they should be working. Anyway, let's move on. We got the answer.
Right.
Don't do it.
Okay. So, well, so if you run this Python script, you should get the same thing as you got with the MPI IO code. Do we have more? Yeah, that's it. So, okay, so let's not go into editing the code. Did any of you finish editing and have a version of?
I haven't run
Hmm?
I haven't run it yet. So
But you edited it.
I
Yeah. So I'm just be lazy and I will steal the other example that I already did. Which was. Here. I have the IO code, so I will just steal it from the other one. Oh. Yeah, so I just have the same code. And so if you run these, actually I don't know, can you run it from the login? Oh, I still have the job. So we only need a single code to run this. And our file is gs.pp. Oh, okay, I started wrong code. So the only difference between a tutorial code and what you find in the GS-ADIOS tool, that is parallel. But it was actually not relevant for this example. So I removed it for the sake of the tutorial. Okay. So now yes, it goes through each step from the information it gets here I see. The first number in the step is the loop inside the plot script. The second one is the coming from this current step of the stream. And the third one is the iteration number as the value of the step variable in the stream. And the min-max is the min-max of the U array. So now we create. So you see, we created 100 PNGs. Produced it, so there is no easy way to look at it, so we don't. So that basically concludes the Python part of the tutorial. And I will just do discussion and go into the in-situ pieces. If you want to continue with playing with the code, right? Then I suggest you look at ADIOS II, which is basically it's the same tutorial code, but it also has the analysis for the PDF card. That does a 2D slice. Well, it takes for the 3D cube, it slices in the first dimension all the slices. So you have 64 slices, 2D slices, and then creates a histogram for every slice. So for a 64 cube input, you will have 64 histograms. And the histogram has a binning that you set at 100 or 1,000 or whatever number. So you get a 64 by n 2D array as an output, as the histograms for this array. And then there is the Python script, the PDF plot, which basically plots you these one-dimensional plots for each slide. So it can generate you plots, but it only takes one slice. And if you run it in parallel, like you run it on 64 cores, the PDF plots Python script, it will read each one will read one of those histograms and make a histogram for you. So it's just an example to learn to use parallel Python. And basically, if you look at the script, there is no difference between using a communicator, and then there is this decom.py, which deals with the ugliness of doing the decomposition for the MPI ranks to decide who reads what. And then otherwise, the loop is the same. Yeah, so that's just the direction how to go to finish on your own the entire training. And so the PDF calc is a C++ code. And if you look at that, the read code is very similar to what you see here. And then it also produces another file. So you reinforce the learning of writing data. Okay. So, and then if you want to look at Fortran, then the other example is the heat 2D, the heat transfer example. So that's a 2D code, not a 3D code. And actually there are Fortran and C++ version of the code that produce data. And then there is an analysis code just in C++. And then we have the Python for plotting. So in the Fortran, we have the simulation. Well, there is analysis code too, right? The analysis code reads in Fortran and then just writes Fortran files, one file per process to print out the values. So that's not doing anything magical. But so the Heat 2D Fortran version is our existing tutorial for Fortran. And you just go through and you see it has implementation of the I/O for Fortran POSIX I/O, HDF5, parallel HDF5, and ADIOS II. So you can even compare the codes, well, and play with them and compare them if you want. But basically, it's a small code. So for performance evaluation, it's not that interesting. I mean, it's not interesting at all. Yeah, so you can have this, and then there is the C++ version of it. That's how we progressed. We had a heat transfer 10 years ago as a tutorial example in Fortran. Then we made the C++ version of it. And then Scott said 2D is boring, I want 3D, so we had to create Scott. So we progressed in complexity, but so you can go back and play with these, and then you can also mix and match working with Fortran to C++ or C++ to Fortran with the simulation and the analysis and see what you get. So that's the difference is there is the column major and row major representation, and you see that there is no declaration anywhere. When you write a Fortran code, you think column major. When you write C++ code, you think row major, basically, hopefully. That's debatable, right? But then it does it automatically for ADIOS just reverses the dimensions of the array. So if you have m by m in Fortran, and then n is the fast dimension, and then in C++ it shows up as m by n. It flips the dimensions, and then so if you just accept that it's m by n, that's how you write your C++ code or Python code, and then you just read the data. There is no need to do flipping at the user code level. Okay, so that's directions for you to play with these tutorial examples. And so let's now go to in situ pieces. So I only have 4 minutes, that's not enough. So let's start a new allocation. So now you get an allocation too. And so you have your example working for you, right? So you can produce a ADIOS output and you can run the Python script and read it. Okay. So what we change here, so now that it was written this way, that they have the same IO name and they read the same config file, we can change the engine. And so my engine was BP4, right? Yeah, so we didn't look at anything in the PDF analysis example. That's how you progress. That's for the other analysis code, how to produce, and in the PDF code, what to read. So we only focus in this simulation output class IO group. Okay, and so if we use BP4, right now we have the gs.bp. We can delete all the data we don't need. So I don't have a data file, and in the we have the source directory, the ADIOS. Yeah, where you have the source file, there is also a shell script for in situ. .sh is the way of running an in situ multiple executables in a single job. So this is the way to launch, when you get an allocation, to launch multiple executables without waiting on each other. So this is simple for Slurm. You can just use the ampersand to launch one, and then you can launch another one and launch another one until Slurm will tell you that you ran out of your allocated slots and there is no way to launch it. So what we use here, we have 64 cores in the node allocated, right? And we launched when we requested the interactive job. So I'm just using 16 for the first one and then use one more for the other one. The other script, did I remove that? Probably. Not sure, maybe I didn't add it there. Then let's not worry about it. Yeah, so there is another one, but we are not using these in this tutorial at all. So let's just learn how to allocate the cores for different executables and then just run these executable. You basically build one MPI-com world from multiple executables. So do you know this trick? Okay, you know it. Right, so we could set up an entire pipeline and just use one giant MPI-com world. That's why, okay, but this doesn't work with the serial GS plot. You would need the ADIOS examples MPI-based Python script. all the examples, grayscale, PDF code, and the MPI decomp.py creates a communicator for its own application. So there would be 4 sub-communicators. Everyone is using their own communicator. None of them is using MPI convert because that spans alien processes. And then you can just run them at the same time in a single application, launch them. And so this works on different machines which don't allow you to launch multiple executables on the same node. But on Setonix, you don't have this problem. So this would be only needed if you want to use the SSC MPI-based engine for doing some code coupling or in situ pipeline in ADIOS. So because that's an MPI base, using you need to have one MPI convert. But since we are not doing anything of this in this tutorial, this is not even copied there. But if you want it, I can give it to you. So let's focus on what we do, because that's the in situ.sh. So we will just run these 2 codes together. And so what we expect here with not HDF5, but we expect here with ADIOS that as the simulations runs and produces BP file, it adds new steps into it. But the Python script can start processing the first step when it's running and then get the new steps as they are being produced. And because it's slower, it will never even wait or wait for the simulation. So we have the allocation, we can just run this. Oh, I mean, sorry. So I showed you wherever you have the source, that you source the tutorial shell script, there is this in situ.sh, copy it into your directory and you can use it. Okay, so you get 2 different outputs here. And so we started up with BP4 and the simulation starts running. And Python takes a while even to start up and start processing data. So we already have like 5 steps produced by the time the Python script opens up, and there is the first step, right? And then you can see that the simulation progress is much faster. So the plotter is way behind, and then when the simulation finishes, the plot is at 1/4 done, and so it will just go through and plot everything. And so then now we should have the 100 PNGs. So now raise your hand if you have run this and you get results. Okay. Right, so maybe on Zoom, can you put the flag up if you have successful run? Okay. Okay, so now we can, so you see, you saw in situ processing through the files, but this is not cost-free. You don't see it in this at scale, but if you have you write data to Lustre or GPFS from a parallel program, and then you have another code running and requesting reading from this data set, even though they are totally different offsets, somehow the file system will slow down the producer. So in practice, at large scale, this is good for developing and setting up your pipeline and debugging it and make sure everything works. But if you are sensitive to performance, you don't want to do this through files. Well, this is the one thing. The other one is processing data through files is slow. So if you want to use network staging just to connect producer and consumer, if you don't want basically the interference with the file system.
Yeah. Well, one of the things that we were talking about the other day is that, you know, they have a shared file system, so then you could run and then essentially visualize the data in a similar fashion. And, we get, that's possible depending upon the file format, but it's really, as you say, it's about variability. How much are you hurting the thing producing the data? Does it slow down? And so I don't
We
see
never had any problem.
how is that possible though? It depends. If it's small amounts of data, then it makes sense. It really depends, and that's why I'm wondering, because no file system can really handle that.
I haven't done that with huge amount of data personally. Maybe Alex is with open phone. Have you had any experience with huge amount of data, like constantly writing within the scratch maybe?
Well, yes, but not doing any post-processing, so just writing results, so it's not the same thing.
Right. That's all I'm trying to say is, if it's conventional hard drives, you have a problem, because you're going to get those hard drives to seek, especially when you're doing this with high levels of concurrency. And that's what Norbert's trying to bring up. It could work small scales, but once you start doing large scales, once you do it when the system is actually really crowded, all we're saying is, like, there's no system that we know of that can handle that. If it's all flash, it could do a much better job though. But if it's not all flash, you're gonna have to worry.
Yeah.
And you can get lucky. And the other thing that we find is, like, you're running your code, and now you do something and you're doing it through files for some in situ viz. No one's really paying attention a lot of times to the time. What if it's 10% slower, 15%? And when you're doing it at scale, again, if it's 10% slower and you had a 20-hour allocation and it was 10% slower, then you care.
That was just sample cases that we were setting up the workflow and pipeline, so we didn't test.
Yeah, so I'm saying it would be good to test.
Yeah.
Because we're trying to offer all these options just because, at small scale, it doesn't matter. Because who cares if you even waste like 10 minutes of time when you're on one node?
Yeah.
But, so anyway, sorry, Norbert, go ahead.
No, this, no problem. This is good discussion. So just let's go next step. So I clean up this whole thing here. No data. Right, no gs.bp, no images. So we set up this pipeline correctly, right? We have the setting the engine, the common engine for producer consumers through the ADIOS II XML, and hopefully with the settings JSON you have the proper file name set. That's because the Python script doesn't read the settings file JSON, so the file name is in the in-situ.sh. So that just has to match. So the next thing to do is to change the engine. So was using BP5 stream or BP4 is the same thing. Can use SST. And let's see what do we get. Right. If we get the, yeah. Just look at the screen. Just want to explain. So now we use SST. And what you can see again, there are 5 steps produced by the plotter, by the simulation for each plotting. The plotter is slower. And immediately what you can see, the GS plot produced 21 output steps, right? And the steps are, there is a big jump, it's a 50. 810, 870, 920, 970. So in this case, we only have 21 PNGs here, and they are not consecutive. So what happened with what happened here, right, is that we run, and there is no data file. So we were purely just streaming from producer to consumer, and the consumer was slow, and the producer threw away into the data what was not consumed. And so the plotter only got we always just getting the latest from the producer. So in this case, we don't block the producer. We want we focus on the producer, want to have it go fast, and then we just process what we can get. This is usually good for something where you are interested in the latest. But if your analysis cannot do this, it would die if you don't get all the steps properly and you calculate something you want to make. That's the important piece. Then there is an option to slow down the producer. And that's in the SST options. So the current setup is saying the producer is not waiting for anyone. So if I run alone, there is no one consuming data. It will just run and throw away every single output step. The second one is saying it only just keeps one step in memory, and if no one is consuming that, it will discard it to go ahead. So if there is a new step produced, it will just throw away the existing one. We can change this policy saying, no, I want blocking, not don't discard, block the producer.
What's your case?
And the other one, you can also say, hey, we have a consumer, I want to get the very first step. So the producer will start first, but it knows that there must be a consumer coming, so it will block, right? So now it will, let's see my keyboard, okay? So with this to change, if I run this thing, well, let's clean up the data. So what do I want to do? Or actually, the sales script does. So what now you can see, they are go step by hand in hand. The simulation was waiting for the plotter to join with the open, right? Make the connection, and then it produces the data, and it will wait until the plotter consumes it. So now the simulation run much longer, right? But now we have all the 100 PNGs. So it's up to you which one you want to do. Who is the important part, the producer or the consumer? And that basically concludes our hands-on tutorial. Well, yeah, the hands-on tutorial, it was already demo, right? Or you did run. Scott asked me to show you one more thing that we didn't talk about, and that's the compression. So ADIOS also has the operators, and we have lossy and lossless compression routines supported. The Pick on GPU WordPress guys really like BLOSK. A serializer is basically using LZ4 algorithm underneath, but so BLOSK is a BLOSC. This is what's used by, it's kind of a fast compressor that can use it's implemented multi-threaded compression to even speed up compressing large data sets in memory from a single core. And then ADIOS does the distributed compression. So every MPI does their compression on their own. So they really like it for lossless compression. bzip2 is a default one that builds and really. That's why we're working. I don't know who needs that, but for double arrays with precision, they don't really do much, right? And then so we also have the ECP developed lossy compressions, ZFP, SC, and mGuard. And so since I found the spec packages on Setonix, ZFP, and SZ, we have that in this example, so we can do that. So the way to use compression is per variable. So we don't just compress entire data set, that we don't have an option for that.
Excuse me, Norbert, I have a question with this. So
with the staging, you mean?
Yeah, you already talked about staging, isn't it? So there is another option of just sort of saving that that is being produced without slowing it that much like this. So staging is,
function call.
I'm a bit confused about what staging is, because I thought staging was to keep the data not on Lustre file system, but somewhere else
Doesn't slow down.
where the consumer can grab it just for post-processing, or I'm completely.
Well, so I'm not sure what you think and expect. So with BP4 or BP5
A few cycles. but-
is a staging through file system. So the producer just writes files
Yeah, okay.
and doesn't have any knowledge about the consumers,
Yeah.
but the consumer can open these files and read the existing steps there while the producer is still producing new steps. So it's the code. We didn't touch the source code since we were producing file and reading from a file post-mortem. This just works through files in stages called staging or streaming the step by step. You can process it. Or there are engines that is purposefully just send data through the network to consumer, whatever the consumer wants to do it, and there is no permanent storage.
You can do it.
Yeah.
So I'm not sure what you are asking for. As you want to
Probably saving the files locally to the node.
That's the point. Does that make sense?
yeah, so that's a different thing, and it's really do we have a local node here? Do we have a on Setonix? Do we have a local SSD somewhere? Is there a pass for here? So you are asking about local storage,
And do I run it?
Yeah, exactly.
for example. So do we have it in here on Setonix, or do we need special nodes or special features?
I haven't used it. I don't know.
To transfer the data.
Pascal is probably.
But it
Pascal is not on the call.
have,
I don't have SSD or NVMe, right?
you can do on these machines.
No, I
I believe we'll have local high-speed storage on the GPU nodes that are coming later, but I don't believe we have it now.
So on the CPU nodes, you don't have as a local.
As things stand, no.
Okay. So yeah, so that's not doesn't apply to Setonix, but for example, what was the browser?
You can just do it fine.
For BP4 specifically, none of the others.
So that's BP4. That's exactly what we're trying to.
For BP4,
That's what we've done.
if you have local NVMEs, you can pass the pass for here to say, but either when you say instead open.gs.bp, you could just edit the source code and say open / whatever, give a pass, and then just you write to local storage. Or you can just tell BP4, okay, there is a local storage which is called burst buffer pass, because other people are pushing for common. So you can change the pass by this, right? So now if I have a local NVMe, like in some on OLCFE /mount/db/ my username, but I have to request in the job allocation to have access to the local SSDs. And so then I can say, okay, use this pass, and whatever I'm saying in the file name, under that, even with subdirectories. And so that's one thing. And the other one, the burst buffer train, could just say false, turn it off. So then if you run the application, now it will write the data to local storage and it does nothing with it. I mean, the burst buffer train by default is true. What it would do, it would in the background, after end step, it will start copying the data from NVMe to your original location. And so this what means BP4 implements on its own a burst buffer support, which is awesome, right? Only problem is for every real application we tried at scale, the draining from the burst buffer to the parallel file system in the background causes inference as much that have exactly the same perceived performance runtime for the application than if you just use synchronous IO, which is a magic to me. I don't know what's the reason. That is basically have zero gain and zero loss. So anyway, so implementation exists. It's useless in this sense, but what you are asking for is just this would be a technology, right? So you could tell ADIOS, okay, just use my local NVMEs, and in the background, please flush it to the file system. So this is not staging, well, not staging between producer consumer. It's staging in another sense that there is a faster local storage, and then in the background someone takes care of it. But since there are no working burst buffer software that we can rely on much, except for DDM company had its own infrastructure and software where it automatically takes care of it, and it's awesome because they have their own networking and storage solution for doing that. So if you have lots of money, you can buy it for the center. But otherwise, there is no generic software that does this. So we have an implementation for it, and we have a bad experience with it. So, so it does work, and that's why BP5, the new engine, doesn't even have this, because we haven't figured out how to do it properly. So this is one way of, I'm not sure if this answered what you are asking for.
Yeah, it was.
The other thing that you could try, and it's shown useful, it has gain. BP5 does asynchronous I/O. So until the end step, it buffers data in memory. And then when your application is running, separate thread like this is doing draining to the file system, but now it's doing from memory, not reading from NVMe. And so BP5 is different.
And the consumer can get that information from memory.
The what? No. So this is just for file. This is BP4, BP5. These things write data to disk, and they don't talk to consumers. Right. But so it just, you say async write turn on. So this only had just a flag. Okay, do this business asynchronously, and this shown some advantage. So this is more promising. If your cost in synchronous I/O is something, this and there are two sides for the I/O cost in ADIOS. As we mentioned, we have lots of metadata. So collecting the metadata from every process, merging it together and writing to disk is not negligible. It's actually high cost. And then writing the data from every data producer process into subfiles has a cost. That this is the part that scales very well, but the metadata collection from all the processes done towards rank 0 and producing metadata has limitations. And this asynchronous I/O, async write, is an independent thread in every process, doesn't do MPI communication at all. So the metadata collection is still synchronous. So in end step, we still collect the metadata, we'll still write it to disk. Well, not write it to write the metadata, but write the metadata to disk. And then every process on its own starts draining data to the file system. In a node, they use a shared memory to exchange data between an aggregator and other processes. So not everyone is writing, just the aggregator, right? One process per node, for example. And so it's basically, for the data writing, it can give you 0% overhead, right? If it's the writing doesn't interference with the application communication at all, the best case you get 0%. So asynchronous writing is completely hidden, but the end step is still kind of costly. The collection of metadata and writing to the, not writing to the disk, but collecting it and creating the metadata data set to write, that takes time. So this is not something like hides completely the ADIOS I/O, but we had like from 5% down to 2.5%, so it halves the I/O cost. And so it could be useful where you have a high I/O cost. If you have an application that writes very frequently, this is not going to be good. So it's only good when you have an application and for it, like every minute writes data, then you have time, if it does some computation, then you have some time to do business. If it writes every second, or then asynchronous I/O is not going to save you anything, because you're I'm sure you were going to interference, plus you not finish the step before the next step comes. So you will have to block the application. So this is another way of doing staging to disk from memory or from burst buffer. But maybe that's not what you asked for. So this could have benefits for some application, but it has to be evaluated case by case. There is no generic rule. How is this going to work? And since you don't have local NVMEs, that's not even really important here.
You can run again, right?
So another one. So maybe you are asking for using extra nodes to stage to disk. What you want is that you want some staging engine that you have producers, consumers talking, but the data magically also ends up on disk.
No.
And it's not as costly as writing with BP4. So we don't have that. And BP4 already gives you this is writes to disk, and then you can read from disk. Now either moving this through network to consumer, but also have a third part somewhere, a third party saving to disk. We don't have that.
I just want to see what happens.
So then in that case, the consumer gets all the data or whatever it asks for, and it has the responsibility to save to disk what
That's what I'm asking.
is deemed as needs to be permanently stored.
Go back to where, show me the viz.
Something in Scott's presentation you're thinking of and referring to, or
No, I was confused about the staging concept with the buffering kind of idea, but yeah, it's fine. I just wanted to see if there is another possible solution of not losing the information that is being generated,
Let's go back.
but also without slowing down, without needing to write it. So something like storing it in memory and the consumer getting it from memory.
yeah.
It is more like a concept of buffering, but
Yeah, so these are the two that I can show
Yeah,
you that it
it's
is
fine.
in ADIOS for BP4 and BP5, two different concepts. Beyond that, we don't have. I mean, the other idea would be is use SST to run a second application as a consumer for the purpose of
What I'm trying to say is.
having a separate nodes. Data comes in and a different application takes care of it and writes
They
to
are
disk.
actually doing really well.
Right, so you like from 1,000 nodes, you stage data
That's why
to
this is-
10 nodes and a different application,
That's what.
and then that writes to disk. And so this application has IO cost. The original application can run freely on 1,000 nodes, only pays the cost of staging from 1,000 nodes down to 10 nodes, right, with the staging SSD.
Right.
And then
That's the thing that.
if it's not too frequent, then the other 10 node application can finish its IO job, writing to disk, and then wait for the next incoming step. And in this case, you can hope that the 1,000 node job runs faster than if it has the IO itself and writing to disk and wait for the IO. But the thing is, the sad story is that ADIOS is so damn good. It scales. So writing from a lot of nodes, your IO doesn't break, doesn't die. So that your thing, well, maybe you are thinking is that the problem is that if you scale up existing IO codes, which was written POSIX IO or MPIO or HDF5 IO, was designed and used for years in up to 100 nodes, and now suddenly a project tries to say, okay, I need 1,000 nodes. And then the IO really bad, right? Because it was not optimized. No one thought about it, how to run this on 1,000 nodes when it was implemented. Now then you, okay, if I could just shuffle the data and do IO separately, then it could be a real gain. But with ADIOS, the IO scales. So you run 100 node, it works. You run 1,000 node, it works. And so the cost is not that damaging to you, right? So staging to 10 nodes has a cost, and then you have a limited bandwidth from 10 nodes to the disk, so it has time costs.
Yeah.
And so the whole setup may give you some gain, but it most likely not. Most likely you would need a lot of nodes, extra nodes, to stage the data fast and then write the data fast enough to keep up with the original application. And so that means you need, let's say, 50 nodes for 1,000 node job. that is 5% IO overhead. That's 5% cost overhead by allocating 50 extra nodes. Right? So you already pay 5% cost ahead in upfront to do staged IO, and you still have some cost in staging to that 50 nodes. So your cost goes up. And 5% for ADIOS is usually a big number. So applications at very large scale, you know, using 5% IO cost is something which is, well, that's pretty high. It's not 50. If you have the original problem that you suddenly scale up your code and the IO cost is 50%, 90%, then of course you can have big gains. But with ADIOS, you don't have that problem.
Yeah.
It's
Yeah, I
the
get it.
same base.
Thank you.
Okay. Well, if I show you the compression, then we can basically, the break will be the end of the tutorial.
No.
Okay, so just let's look at that. So you look at the XML, there is some comments for the PDF analysis, and we can see. So these are options. So if we want to compress we do compression per variable. And you can pick what compression to use and what options for the compression path to compress your data. So we don't have an option say compress all the variables. The ZFP SZ wouldn't know what to do with an integer variable or so you have to set it up for every single variable that you want to compress. And so it's basically this setup, right? Variable. So we could specifically say in the simulation output, not in the engine, but outside of after the, not engine option, but IO options, and say, okay. For the variable U, use the operation called SZ and pass a parameter called accuracy of 3 digits. Since it's a double array, this is a very big cut on data set. Right? So remember, we had a 200 megabyte so let's produce some file. So now if we run our job, there is no difference what you can see here, of course. We are going to produce the data. And if we do BPLS, still have 100 steps of 64 cube, right? But the size is 32 megabyte instead of 200 megabyte. That's because the variable U was compressed in every step. So it's using up much less space. And when we read it back, you get back some values. This is the center 2 by 2 by 2 cube. Now I don't remember what was the original one, but what you should expect to see is that the third 3 digits after the dot should be the same as in the full size, and then you have the other digits, which is, so you get a 3-digit accuracy for point-wise by SZ. That's what it guarantees you. And you can do this with ZFP, or you can do this with mGuard. I mean, and you could also use lossless compression, and you should get the same accuracy as the original one, but then you would not have 32 megabyte. It would be like 190 or 180 megabyte. It will only save a little space for you. It's only good when you know that your space has lots of the same value, like 0. Then lossless compression can help you a lot. Okay, what else? Scott, do you want to say anything about compression? So I just showed them compressed it, the size is different.
Well, I mean,
In staging,
Okay, so-
usually, Oh, okay, sorry. No.
So there's a few things that one could ask the question, which is, we put minimaxes. We put, again, the size of the array. Norbert, could you do the minus capital D on this?
What do you want to see?
Capital D. Right, so one of the things is, it looks the same, right? The question, like in this example, like one of the things is like, when you compress data, what the first thing you see is, here we have 16 blocks. With 16 blocks, if you don't compress it, the size of each block's the same, right? Same number of elements. But when the size, when you compress it, the size of each block will be different, correct? In fact, some of them could be close to 0. I mean, if data did not change, like a lot of times there are areas. So this creates unique situations for I/O, for data movement, because you have to see that. The other thing is, like, when we're putting in the min and max, and I can't remember what we did, Norbert, so this is also to you because I just don't remember. If we compressed it and we did a bit level compression and only have 3 digits of accuracy, then what is the min max showing?
No, the min max is actually the original data.
Right. But that could be different than actually the real data. So that
I mean,
could-
what's in the compressed data?
right,
Yeah.
in the compressed. So there's all these little things that one has to pay attention to when you compress data, depending upon how much accuracy, if it is lossy, and also depending upon the imbalance that you've just created. Because if you're staging it, and now you thought like you're going to get an even distribution if you're staging from 16 blocks to 2 blocks, and if you did this, the first one got blocks 0 through 7, then what if they were all 0 and now you're getting practically no data? And again, you have different things that happen that you have to pay attention to. So we have it available, but once you start working with scale, we're really anxious for feedback, because this could create interesting situations. And interesting in this case could be either good or bad. Does that make sense?
Yeah.
So are you guys interested? Like, everyone in theory is always interested in different types of compression. The other is speed. And again, I think, and I can't remember this, I know it sounds silly, like, I think we can allow compression on the GPU with the GPU aware stuff, correct, Norbert?
Yeah.
So that's the other thing to pay attention to, like, you're on the GPU and compressing those routines can work really fast. So now you compress on the GPU and you're not introducing anything about GPU aware stuff, right?
No.
But we should talk about it just very briefly. So all this stuff is related. So do you want to mention GPU aware real fast?
Yeah, so I don't have any slides on it, but so
Right.
the GPU, the idea of GPU aware ADIOS is that if you have data on the GPU, in this example, we had everything running on CPU, the computed data is on CPU, and we hand it over to ADIOS for I/O. Now, when you are on a GPU for I/O libraries, the only option that you could ever do is to copy back to the CPU first, and then hand it over to your I/O library, right? No I/O library is GPU aware. So what we started to doing with CUDA, specifically for NVIDIA GPUs, to use CUDA, so you can pass a pointer on the GPU to ADIOS and say, take care of it. Right, so here is my data, and ADIOS is going to buffer it on the CPU for doing I/O. So it's not writing from the GPU memory directly to disk, because that's a different technology and it's not existent, or no, it's not something we have. But what you can save is to make a copy on from GPU to CPU by yourself. Instead, you just convenience to tell ADIOS on the CPU that, hey, put this variable and a pointer points to CUDA. I mean, it's a CUDA allocated pointer on the GPU, and then ADIOS is going to buffer it for the purpose of I/O. So that was shown to save some time, nothing stellar, because but if you have lots, many gigabytes and the GPUs are growing and you get more memory, this is one way of shaving off a little bit of time that is part of I/O time, but it's not I/O data going to disk. It's the preparation to move data to disk. So, there are other efforts like the promise of unified memory, then you don't ever need to worry about this. From the current machines that have unified memory, the users who are really using it and pushing to the scale, we get the feedback that they are not using it because of performance reasons. So they are still ending up separating the host and device memory on their own and managing it instead of relying on unified memory pointer magic that is supposed to give them convenience and not destroy performance. So they choose performance and then they go to the trouble of using it. But in the future, maybe this will be completely irrelevant question for, you can just pass any pointer and the CPU will see it the same as a GPU. But if it doesn't, so then we have a CUDA version for this, and then we are working on using Cocos under ADIOS to use any kind of GPUs, plus Cocos pointer. So now if you have an application using Cocos, you could pass on Cocos use to ADIOS to write data. Otherwise, you could just pass pointers and then we use Cocos underneath to grab that pointer from any kind of GPU and download the data ourselves. So it's new. We are having this in CUDA. It's working. It's in the 2.8 release. It was already in 2.7, but don't have too much experience with it, right? And the known complexity is that for GPU programming, you tend to have a different data organization. So your data is is it called? Stored block by block, optimized for the SIMD size of the GPU, the actual GPU. So you have a number in your source code somewhere saying how many elements in a row should be put together on the GPUs to speed up the GPU loops. And so the data doesn't tend to be not the same as on the host memory. Basically, this is the starting premise of Cocos, of showing that the problem with GPU programming, writing programs that both work on CPU and GPU, is basically that GPU prefers column major ordering, the CPU prefers row major ordering, and they show an example where you have 10x difference for setting that. So of course, give you a big incentive to reorganize your data in memory. And so that gets complicated, and so now it's hard for ADIOS to figure out what is actually your data versus what you are declaring to what you want on disk. So that's where we see the trouble for us, or we don't know how useful this feature is, that an I/O library is GPU aware. When we talk MPI being GPU aware, that's a feature of MPI where you can send over data from one GPU to the other one. And so you avoid the problem of different data organization in memory because you most likely want to have the same. So that's a nice thing for MPI, but for I/O libraries, it's not clear if it will be very useful. Okay, that was a too honest answer. Should have advertised. Yes, we have. Could ever GPU ever I/O. Please go ahead and use it and report to us if you see issues with it or if you are happy with performance gain. Okay, so I guess we are done. We are done, not just break, but we are done. So now we just can have discussions with about whatever we want. You tell us if we missed something and you need more information on something.
On your WSL, Norbert, can we, no, we can't show the visit peer review.
I cannot show that, but so the one, no, okay, so one thing that I can attempt to go on the Amazon server, and I cannot show the ParaView GUI magic, but I can show.
Catalyst.
Yeah, so one thing that we didn't talk about the engines. So we have lots of engines, and
That's nice. That's really cool. Amazon uses that's nice to see.
Yeah.
As a remote.
so I have we have a tutorial set up for. The point is we have many engines, and Hitware is the company who has a vested interest in ADIOS. They have been working with us from the beginning of ADIOS to development. They are doing all the CMake magic and the C-test magic. So we have like 2,000 tests run for every commit on 20 different virtual machines, different macOS versions, Windows versions, Linux versions, Intel compiler, PGI compiler, GCC compiler, whatever you have used. So all these combinations to make sure that ADIOS is really a stable code and you don't break it at all. So for example, they are pushing that we must have Windows support because ParaView is a tool that users can use on Windows. And so if you would copy an ADIOS file onto a Windows laptop, you should still be able to open it and read all the data as the way you want, right? Even including the compression and stuff. So we have full support for macOS and Windows and Linux versions beside the supercomputers. And the other cool thing that they came up with is the plugin engine. The purpose of the plugin engine is to have is similar to VTK and ParaView and stuff that you have a software, you installed it somewhere, and now you want to add your own thing into it. So you can develop an entirely new engine and just use an ADIOS installation and say, hey, use this my engine for my purpose. That's not for users, this is for developers, right? And the use case for this is that now if we have an ADIOS installation, the upcoming version of ParaView, the next version 5.11 that's coming, builds a specific engine using ADIOS for the purpose of inline in situ visualization. So if you know Catalyst or libsim for visit, or if you know traditional, I call it traditional in situ visualization, is that you run a simulation code and you add Catalyst or libsim function calls there to process data and make visualization and save images to disk. So this visualization runs inside the simulation itself. It's part of that. Well, it's a simulation, a visualization step inside the simulation. And then conceptually, what we have IO steps. It's kind of natural thing. Okay, can I replace my file IO if I'm doing some kind of IO just for that I'm going to visualize? Just do visualize it, and then just produce images on the fly. But now, yeah,
that's when you may miss a few frames, right? Because the simulation is doing the visualization.
No, but wait, no. Traditional in situ visualization is you add Catalyst or libsim calls into your code, and you do visualization as part of your iteration loop. So every frame, every output step, every 10 step or every 1 step, whatever, you are going to do visualization and you save images and it's there.
Which is expensive.
Which is extremely expensive in our opinion, but it's one way of doing in situ visualization, right?
Okay,
You already, I'm starting to warm up the presentation and you're already killing it.
I mean, look, we've worked on, and continue to work on all these different, I want to say, papers, creating models, really understanding this. And the thing is, I keep trying to say it's really a workflow that you're trying to execute. So when you talk to the majority of the visualization crowd, like we do, okay, and again, I'm just saying, if all you're doing is an ISO contour and you have a parallel code running, that thing will parallelize really well and work really well. And you can work with Catalyst in situ, and it's great. And you can show that's better than taking the data, which could be really large, sending it over from all your nodes to a smaller set of nodes, and then visualizing it. In other words, why move the data to the work? Just have the work to the data. Okay. And again, these things scale really well. Now let's take that and you're trying to do a streamline. So imagine you have a domain decomposition across 1,000 nodes, like in CFD. And now you're trying to do a streamline. And if you're trying to do a streamline, you understand that there's going to be attractors, there's going to be vortices. All of a sudden, if you launch, let's just say 1,000 streamlines, imagine like in this room, what happens is that with the error flow, things go really concentrate here. You have your domain decomposition node with all your processors, and maybe it's a 2D or 3D. After a little bit, just a few of the processors will work, and you're just passing around small amounts of data constantly. That's going to scale horribly. So you would never do that. So look at all your different algorithms. Once you have a bunch of things you want to do, now you're going to slow down your code a lot. So if it's one thing and only one thing, Catalyst will work great. Once you have a bunch, or you have some complicated routines, once you start doing that, now it's like, it's hard to say. Traditionally, we find this staging approach does work better for the majority of routines. And then you have your choice. Do you slow down the code? Or do you just say, visualize wherever you can visualize? We want to offer all these choices because there is no one single answer. And, and I mentioned it in the beginning of this. It's easy to say the one is better. And people can show like Catalyst is best. And they show it running off of like one node, and they're showing some toy application. And of course, they're going to be right. Then they go to 100 nodes, and then all of a sudden, most of what they say is wrong. So with kitware and stuff we're doing with, the ParaView guide, we want to offer all these options. I mean, I hope that just makes sense. So and that's the stuff that we have. And like all options are really important too, like in all the staging options. Like we would love to say you should always do RDMA. Okay, so we started this. You can look at my history in this. And again, it was like 2005. We were doing RDMA. Do you guys know what RDMA is? No?
Mm-hmm.
Okay, I'm going to give you a bad answer to this. It's remote data memory access. And my bad answer is like, in theory, what it really is like you're on a node and now you want to access memory on the other node and you can do this zero copy. Okay, it's a very low level protocol, right, Norbert? That's what the network fabric uses. So you've heard of MPI, I guess. What do you think MPI uses? RDMA. The fallback of RDMA is things like UDP or TCP. So in ADIOS, in SST that Norbert was talking, we have now what can run under it, which can be TCP in the worst case, or
reliable UDP. Or you could run with RDMA, or you could run with MPI. And of course, which one always works better? Which one do you think?
The lower level.
The answer is, it depends.
If better means totally reliable and working everywhere, then that's TCP, right? There is a reason why TCP is so resilient,
Right.
staying
I mean,
around. And
in other words, we're trying to achieve something that is similar again to what you're showing. Like, all we're trying to achieve is a simple thing. The philosophy is you launch your application, like what Norbert's doing, you launch this application, and then if you want to launch your visualization, you launch it. The Catalyst way is, well, you got to change your code. You got to compile it in. Well, that's not good for many cases. The other problem again is the speed and other issues. The one thing that the Kitwares guys solved for us was you have your code, and now all of a sudden you could run, if you have ADIOS in your code now, you can run Catalyst without changing your code. I mean, that's the beauty of it, is that it just has some ADIOS puts. Your other code has ADIOS gets. And now it just memory reference between them, but you don't have to put Catalyst APIs. And why is that important? Well, if someone cared, you can do that with a similar library called libsim. And now you wouldn't change with libsim, it would be the same thing. So don't change your code. And then all of a sudden it's like, well, then you can run it here or there. So we're trying to offer all these options because there is no one set answer, especially all of a sudden it's like someone wants to connect over the wide area network. And now if it's purely in situ, and it was part of my question, when I say, like, well, what happens if the connection drops? Have you ever been, say, in a room where the lights go off? Like, do you want the whole simulation to just hang and not do anything? So you got to be really careful, especially at scale. So again, it's like, if you're not at scale, you can do a lot of things and not care about it. And you guys obviously at Pawsey have to care about this at scale, right? But it depends upon your users. We're just trying to give flexibility, right, Norbert?
right.
And the final thing to say with the compression is, yeah, go.
No, because staying in this topic, turning back this into the other application. So Scott said, one option is if you have ISO contours, scales, you have visualization that scales well, it's beneficial to put it into the code which is running at scale. If you have some algorithm, not just visualization, if you have some codes, applications usually suffer from that. And we have with XGC, for example, been designed for scale, been programmed for scale, and then different scientists add different new features in there, right? I need this calculation. Scott showed some in his presentation. One of them is very costly and doesn't scale. So the F0 data calculation was costing 30% of the runtime just to have that data calculated and output. And the reason is because it doesn't scale very well. It's you need lots of communication between processes. So just like with the visualization, can we move this out from an application to another side?
Example is incorrect, but go ahead.
I thought it was the F0, but yeah, okay.
Just go ahead.
The point is, in applications, you may find that when you want to scale it, that there are specific parts that are not very much the.
Just wondering if you guys are taking a break?
Since we are wrapping up, basically, that's why we don't want to take a break.
Right.
They want to take a break, but we don't let them.
Okay. Are you being held hostage? So I need to do something drastic? No?
Yeah, soon we will. Soon we will.
Okay, you're fine.
But then you'll finish early, so that's good.
Yeah, so basically, as the question is, if that's not part of the core calculation, but it was added on as extra analysis that the user, I always want this, I wanted to put it here, but now I'm paying too much cost, then you might say, let's write a separate program for just that and use SST like staging and run it on an extra 10 nodes, which is its sweet spot for scaling, right? So there is no point to scale it to 1,000 nodes when the performance dips.
I can't do this.
And so even for a code like Fusion, XGC been for two decades of the code existence, it's always been designed for large scale and it was always scaling at the largest. They also have this problem occasionally popping up. And then our colleague demonstrated saving 30% of runtime by moving out and paying 1% cost for allocating 10 extra nodes over 1,000. And so decreasing runtime from the total cost of your using resources 30% to 1%.
Can someone help me get on Zoom and then I can just share my screen?
Right. So
Or
well, yeah.
are you on the Fusion paper? You're on it, right?
Yeah, but if you know where it is, you open the yeah, just find the Dropbox.
Where's
No, we
the?
are on a different screen.
Oh. Okay.
Yeah, you can use that mouse and keyboard.
Oh, thank God.
Right, so that is the same thing. Having
You can
multiple
log on with
options.
overlay, though.
Oh, on Firefox I can.
Is this Firefox?
No, that's Edge, right? This one I.
Oh, okay. I'll get it. Go ahead. You can do your rant and raise it.
Okay, I do.
I'll just show.
So basically that's it, right? So that having all the options, going from what we call inline execution, that is the consumer is, so we have an inline engine in ADIOS. The purpose of it is that it's running inside, the consumer is running inside the producer. So it's nothing else than the end step. The puts will remember pointers and the end step, then run the consumer, and the consumer's gets will just get the pointers that are already there. So there is no copy at all, and the consumer can do whatever it wants, including messing up the pointer data. Probably it gets const pointer, so it doesn't. But oh God, the Catalyst engine is using this technology so ParaView now can go inside the application, get access to the data, and then do visualization and do what Catalyst do. So it can either write images or connect to back a GUI and do interactive in situ visualization. So that's the idea. So that's one option, inline engine. Second one is when you run separate.
Which is still expensive, the inline.
Well, yeah. So that's that. We are not arguing against that. Is that it's an option, and it maybe if the user that's what it wants, this is an option to use, right? But what if they want to move to? So there is a user at the Japanese Space Agency whose run is the visualization is not an option, an extra option. It's basically the thing that he always does, he always wants to do, and they have a separate cluster to do visualization. So move out data from the supercomputer and then have LiveSim-based visit, interactive visualization sessions, as well as batch simulations. So they always start up simulation, they set their views, they see what they want to do, and then they say, okay, let's run these and produce me the next 1,000. It runs for whole day, whole night. So that's the option, but then it's writing the tool, the application on the cluster, it's still could be an application which using inline in situ, right?
So this is a paper that's being presented in Germany next week. And, I mentioned this is all really dealing with what we call with what happens when you really deal with real applications and they're running at full scale. And they're trying to do a lot of things. And the thing I'm just trying to see if, I guess, the cursor. So essentially
this is a cross section of a fusion, reactor. This is either, so this is a two-dimensional plane. So think of this plane just goes around like in a donut. Okay. And what we're really concerned with for confinement, you can see this thing marked diverter planes. And what we're really caring about is how energy comes over through turbulence from the core of the reactor over to the edge. And this is what we call the strong side. So think of this as like inside the donut and this part's outside. Okay. So what you're really caring about is what happens here. And what we're trying to do is we're trying to put, just like in an experimental reactor, we're trying to put in diagnostics to see things, but we're not trying to switch the code. And what we're really trying to understand is as these energetic particles come over from the core over to this region, like in this thin region, what's going to happen past this X point. And again, this is like where you think magnetic reconnection, but this is where all the interesting physics. So what we did was we put in a series of codes, analysis codes. These are the algorithms, and you can see in this case, we only did 3 algorithms. The first one was computing what we call a Poincare plot, a surface plot. So essentially, if you're familiar with streamlines, here you have a magnetic field, and what you're doing is you're advecting your particles. It's a very expensive calculation in fusion because you need to guarantee that this is divergence free. Okay, so tiny little errors, not good, because they build up, because what you're doing is you're advecting a particle that goes around the torus, and every time it hits this one plane, you're going to mark it, and you're going to mark it. So you're going to keep marking this plane, and then you're going to see the structure in there. Like, for example, in magnetic islands, or things which are stochastic. So if you remember from simple magnetism, like, with a simple magnet, you should trace out an equilibrium, and you should just have closed surfaces. But due to all these different effects, like magnetic mirroring, you're going to get islands or stochastic regions. You're going to get strange things to happen, especially around that thing we call the X point. But this is a very, very, very expensive algorithm. There's other types of diagnostics for looking at the fusion, looking at heat load. These are not as expensive. So some of these things can be done at different locations. So this is what we did. And again, if you can see that the first thing is, like, you can see we're only scaling in the case we ran for this paper up to 1,000 summit nodes, but it's still like 25% of summit, which for some people that is large. Okay, for most people. And when actually things are occurring, you can see a lot of the time being spent in different diagnostics. These are just the kernels of the routine. Okay, and in even time steps, it's due to what's going on in the numerics, you're doing a bit more calculation, which is why we separate out even and odd. But this is showing in figure 3 for this Poincare, this is how things scale. And again, when you see the time per plot, and it's the number of puncture, what this means on the x-axis is, remember I said you're going to go round and round. Every time you hit, that's 1. So 125 hits is not a lot. You want at least 500 hits. And now what you can see is that, in this case, on the red case, okay, you still get like hundreds of seconds. Okay, and this is done on the GPUs. So this, you can't just even use and put everything on one GPU and do that calculation. We need several so that when the simulation runs, and you can see the time it takes, rotates between 60 seconds. In this case, it's whatever, 80 seconds. So this is not acceptable, right? If this was purely in situ, in memory, the calculation for everything would take
somewhere between 60 and 80 seconds. And then to do this one simple diagnostic, you would be hundreds of seconds. That's not acceptable. So this is a clear case. In other things that you can see, you can make it actually the cost to be really, really small, right? You can see these times are like in like a few seconds. So that's why you have to think of the entire workflow, and you have to think of the scaling of this. The other thing, like what we're trying to say is, this is if you're writing the files in figure 5, and if I can just make sure you understand, like, hey, this is now, we're doing staging with files. And again, it's just writing files. On 256 nodes for this run, the variability is really small, right? We're pretty good. For 512, well, your time takes somewhere between what, 80 seconds and 90 something seconds. Is that a big deal? We would say, yeah, it's a pretty big deal, right? You really don't want that. And then of course on 1024, things work pretty good. And that's just the variability, and things could change a lot. So by using this in memory, you can greatly reduce variability. And the other plots are just showing, you know, some of the different things in the physics. You know, I showed a movie of this because there's some new effects here that, because we have all this extra diagnostics, we can see. Because it's like the thing like all viz people want. You want to be able to visualize like everything all the time. That would be perfect and for free. But there is cost. How you do it, where you do it matters. And what we're saying is we're trying to give people a lot of the flexibility to add things in these workflows. And that's really what this paper is all about. Like, how do you do that? How do you actually create, you know, in some sense, even a model to understand the time it takes to do things? But, you know, it's just like one result, but it really shows the importance of all the things that people want to do, from the different calculations, numerics. And we need full flexibility from files because you have persistence. So sometimes you need it, and sometimes once you start running at scale, you need performance. So that's what I wanted to show here. Okay, does that make sense? So I should point one more thing. We were originally going for a Gordon Bell nomination, if you guys know what that is. Like in HPC world, like that's like the ultimate prize, and it's really about scaling. So like, you know, everyone wants to win one of these. And as I said, the problem for us was we were doing this and we were optimizing the simulation a lot on these GPUs. But then we saw this plot and we saw this, and this was not what we expected. And that caused us a year because it's only once a year. So now what we're doing is we're actually increasing this workflow just a little bit. Norbert mentioned this F data, and that was the stuff I talked about when I gave my talk about like histogramming, like a 5-dimensional histogram. And that reduction routine, once you want the errors to be like floating point accuracy, all of a sudden that takes like 60 seconds. And it just so happens, like, you know, as I showed on here, that's like 60 seconds. So now we have to put in more in our workflow. And if you just said everything's going to be traditional in situ and just tax on the cost of a time step, you know, we'll put more time in our diagnostics in the simulation, and not, and you can actually scale down a lot. And that's what we're trying to do. So we're trying to do this for many applications, but this is one good example. Norbert, you can say whatever you want now.
That's it.
Any questions on anything we presented? Any feedback about ADIOS? Or not yet? You'll give us when.
Not yet.
I had some questions if you can fit me in.
Yes, absolutely.
Awesome. I remember from yesterday you were talking about partial writes per step of, you know, large array type areas and in multiple processes. In terms of the storage of these guys, it's still essentially designed around that array being mostly full. It would be poor usage to have sparse writes essentially to this area.
Just repeat the question. I must have missed. Sorry.
I think I phrased it poorly, sorry. I remember yesterday there was an example of multiple processors writing windows into an array, and that they didn't need to cover the entirety of the array. Yep. Nonetheless, I guess the efficiency of having, say, a poor coverage of that array comes down to how it's being stored by the engine in the back end. Again, I'm thinking of this weird application in the back of my head. If we had very sparse coverage of a large array in a step, will that be stored in a space efficient or a space inefficient manner?
Well, you could. You only store it in space efficient manner. They have no option to store the empty spaces. Well, one option is to use the HDF5 engine, and that would be very inefficient for you. So if that's what you are looking for.
I mean, what? So let's go to different levels here.
Yep.
This is where.
Close that one. Close these PowerPoint because we don't need that.
I'm just trying to show this, but I'm really struggling here. Oh, I see it.
So the zoom is on top, so it covers that.
What slide was this, Norbert?
Let me look for it.
Okay, so let me try to explain this. There we go.
Yep.
So I'm going to explain it multiple ways. Norbert explained it. So maybe between both what Norbert said. So basically, in these different rectangles, here you're defining some global bounds. So let's imagine this global bound was, let's be very simplistic, 1,000 by 1,000. Okay. Well, each one of these blocks, when you're writing it, that's a dense representation. So now what happens is that each one will write that. The metadata is going to then say, okay, Norbert's trying to point.
He doesn't see the screen, so.
Okay, so I'll point and Norbert will move the pointer to where I point. So we're tag teaming here. So if I point to this block here, what happens is that's going to be dense in storage. And then what's going to happen is that the metadata, which describes the offset from the bottom to the top, that's the Y offset, and then the X offset, which is going over, that metadata is then going to have it such that that goes into the file. So for each one of these rectangles, the metadata will be there to say where it lives in the global space, and then all the storage will be dense. So as Norbert said, that's efficient, correct?
Yep.
So that's partially correct. Okay, I always answer my own questions. And what I mean by partially correct is, now let's suppose that in this red region, it's really super smooth. Okay, but let's imagine in the middle region, in what is that, yellowish, greenish color. Okay, so in this region, now imagine that thing is very stochastic. Well, if I can compress it, even with a lossless compressor, this can actually compress well. I'm sorry, whatever region we said was smooth can compress well, and the other region won't. So now all of a sudden, you're actually now going to compress, and then you're going to store that, which will be dense, because that's what we're trying to achieve. We're trying to remove that. Then, like in the presentation I gave on Tuesday, I was talking about you can then produce multiple views using this mGuard system, which means that even on each one of these pieces for each variable, you can start having then different views, which would then have less degrees of freedom or less points on each piece. We're trying to have this avoidance of just hey, this is a large array. So Norbert's comment, okay, is, well, if this was HDF5, you have your hyper slabs and you have your global space, right? And everyone's going to put that, but it's got to have storage for the entire thing, right? And now all of a sudden you have a nightmare if you have more white space, but in even this case, it's not good. So you will waste lots of space. So we're trying to avoid it. The other thing that I don't think Norbert said, now again, I hope I'm technically correct on this, so Norbert always will beat me up if things have changed, but what he's not showing is, well, actually it's showing here on this, that's on the overlap, we're gonna have the data multiple times. In HDF, it will only be done once. But if you actually put the data, in some of these cases, it could be from multiple processes and it's all the same. Which is the correct one? Is it the first, second, or third? If we store all of it and give you the ability, although it's low level stuff, but if we give you the ability that you can access any of it, at least you have any of it. But in their case, it would be like what? I think it's the last one or the first one that comes in. I can't remember, but it's one of them. We're gonna have all of it.
The last one who writes.
And right, the last, right. But for us, we'll have all of it. So if you really wanted to get it, you could. So we're just trying to give you a lot more flexibility. So that's the whole sparse dense thing. So I think we both answered it. Hopefully.
No, you've answered it extremely clearly. Thank you very much.
Yeah. Any other questions?
What is this? That's in the middle, on that is it.
Then just go all the way up where it says stop share.
Yeah.
Well, thanks for spending the time listening to us.
That one.
No, I got the stop share. I just want to bring up the screen
Oh,
of Zoom.
that's this one.
Oh, it's here. Okay, I didn't find this one. Okay.
Well, I guess we'll end and do you guys have our email address? Norbert, can you just put that up on the screen since you're sharing our email addresses and put the ADIOS page so everyone knows. I mean, I can't believe they don't know by now where everything is. But you know, you never know.
The email is here. Was here.
Yeah. So Norbert and Scott, thank you very much for delivering the tutorial and also the lecture the other day and all the visits that you have made with researchers here in Perth. That was a great opportunity for us to learn more about ADIOS and also meet you in person. So thank you very much for visiting Perth and delivering the tutorial.
All right. Thank you.
Thank you.
And thank you everyone for joining us as well. All the participants in person and online. Those in person can now move to another room where we have prepared something for you. And those online, thank you for joining, and we hope you'll enjoy the rest of your day and the week as well.